All right. Thank you for the introduction. Thank you for the introduction. So today, I'm going to talk about my research project where I monitor multiple cellular networks simultaneously using a single radio. So first, let's talk about the components in a cellular network. And in every network, you're going to have at least two components. You're going to have the cell tower and one or more devices within the network. To attack this network, we need a device that transmits on cellular network frequencies. And so in the research community, we often use software-defined radios to rapidly prototype cellular network attacks. And these radios have the capability to either transmit to the network, receive information from the network, or man in the middle a device communication. And so one example of an attack that I'm going to use throughout the presentation today is a device counting attack where the adversary aims to monitor the number of devices that have active ongoing data transmissions within the network. Most existing cellular network research assumes this simplified model where there's just one tower, one or a handful of devices, and one SDR within the network. But in the real world, it's a little more complicated than that, because in real world networks, in real world deployments, we don't have just a single tower and a small number of devices. We have multiple networks all sharing the same tower. Each of these networks are going to service hundreds or even thousands of devices. And to prevent your call from dropping as you transition from service areas, you're going to have multiple towers for each of these networks that have overlapping coverage, so your call doesn't drop as you move through free space. So in this work, we're going to talk about how do we monitor all of these networks simultaneously versus just doing one network. So how can we do this? Well, one option is you can just buy more radios. There are a couple of pros here. It is simple to engineer and you get full-time and frequency domain coverage. However, there are a couple of issues with this, particularly cost. It is difficult for a research lab to purchase enough radios to be able to monitor 10, 20, or even 30 networks within an area. And worse off, powerful adversaries are not cost sensitive, which leaves research labs effectively outgunned. One such an example of a radio that can monitor all networks simultaneously is this Cyan HB here, which costs $162,000. A powerful adversary could also just buy a bunch of USRV B200s at about $1,300 each. But as I said, for a research lab to replicate the number of radios necessary to monitor a whole area, it doesn't really hold up. So we need a better solution than this because research labs can't replicate the scenario. So how do we get around this issue? Well, in this work, we're going to propose using a single radio efficiently by multiplexing it to listen to all cells simultaneously. Now, I say simultaneously, it's not actually listen to every cell simultaneously, but I'm going to get into that in just a moment. So how do we monitor multiple networks simultaneously? Well, our key insight is that in LTE networks, every single data transmission is tightly scheduled and occurs at predictable times. So, and in addition, we only need to monitor a small number of data transmissions in each network because most of the data we aren't interested in. We're only interested in a small fraction of data. So on this resource grid that I have drawn here, we organize signals in time and frequency and draw them on a grid so we can keep track of them. Let's say that the signal of interest that we want is just the two red stripes in subframe 0, and that's all we want to listen to. So if that's all we want to listen to, then we only need to be tuned onto the cell to receive that signal. Any other signal that's present within the cell is irrelevant for our purpose. Now, there's one challenge that we're going to have to overcome when we're monitoring multiple networks simultaneously, and that is synchronization. Because transmissions from multiple cellular networks are not synchronized in time. Everything is synchronized within each network. However, between networks, we are not synchronized. So one eNode B is not going to transmit a signal of interest at exactly the same time that another eNode B will transmit the signal. So this causes these signals to occur at different times. So if we can tune the radio fast enough, we can listen to all of the signals of interest here. So in this example, we'll first tune to network A and receive the first red stripe symbols. And then we'll immediately issue a tune command to the radio to tune to network B and receive those signals, and repeat so on until we get all the way through the system. Now, I want to come back to synchronization because that's another challenge. We have to synchronize with each of these networks, even though they're out of sync. So in LTE, the primary method that this is done is using pilot signals called the primary synchronization signal and the secondary synchronization signal. In SRS-RAN, which is the dominant LTE resource platform and the platform we built our tool on Intercellular upon, it uses a three-stage pipeline where it first searches for the PSS, then it searches for the SSS and checks if it's subframe 0. And if it is, it will indicate that the frame is aligned. But if any one of those steps fails, it goes all the way back to the beginning. And this is a problem because, as you can see, there is a lot of opportunity for us to go back all the way to the start, which means that synchronization takes forever. We measured the amount of time it takes to start the tune request to when we're able to receive meaningful data from the cell, and that takes about 336 milliseconds to complete. So slow synchronization is a barrier because if we move too slowly, then we're not going to be able to receive all the signals of interest from all the cells. So we needed a better solution. And so I developed a rapid resynchronization algorithm that uses time rather than the synchronization signals. LTE is highly structured, and that means that signals will occur, the frames are structured and they will occur at predictable times. In LTE, every frame is 10 milliseconds in length. So using that, we can use one frame, the time of arrival of one frame, to predict the time of arrival of another frame in the future, even if we have not been listening to the cell for a long time. So our system does exactly that. When we're ready to tune off of the cell, we save the time of arrival of the last radio frame that we decoded. And then when we're ready to tune back onto the cell, we calculate the time of arrival of the next radio frame. And doing that allows us to skip blind synchronization. Our system, though, is designed to fall back to blind synchronization using those pilot signals in the event that this synchronization method fails. So let's talk about performance here. So I said that PSS and SSS-based synchronization takes 336 milliseconds. Our system, Intercellular Rapid Resync, cuts that down to just 176 milliseconds. It cuts it down by nearly half. And most of this time is spent just waiting for the radio to retune, which takes a significant amount of time. And because this is a time-based algorithm, we wanted to make sure that our system was stable. So we quantified how well our system works depending upon the amount of time we spend away from the cell. And because if the sense of time on the network and the sense of time at our system drift at all, if there's any sort of clock drift, that destabilizes our system and will cause a synchronization error to occur. What we found is that synchronization time does, or synchronization probability does decrease as the amount of time you spend off the cell increases. However, at 2 seconds, we still had a 93% success rate where we didn't have to fall back to PSS and SSS-based synchronization. And even at 30 seconds out, we had a 68% success rate. And finally, moving back to the example that I mentioned earlier, where we were doing device counting, we applied device counting to our multi-cell system. And what's shown on the graph right now is what you would expect the naive performance to be. So approximately 1/n, because you're splitting the amount of time that you're listening to each cell by the number of cells that you have. So this is what you would normally expect it to look like. And I'm also going to define coverage ratio here, where the coverage here is the ratio of the number of devices that we detected versus the actual number of devices present in the radio trace that we had. We simulated a radio trace with 235 UEs and ran it through a decoder in multiple systems. And these are the results that we had. We found that by intelligently scheduling the radio, we significantly increased the performance over the naive performance expectation, where we went from only a 10% performance listening to 10 cells simultaneously to over 90% by just listening for only the signals that we're interested in. And even when we brought it out to 50 cells, we still had a greater than 35% coverage. That means that 35% of the devices that were present in the cell were actually detected. And 50 is a ridiculous number of cells, although it might not be in the distant future with 5G microcells or picocells. But even at more reasonable values like 10 and 20, you're still getting extremely good results. And so what our work has done here is we demonstrated the feasibility of using a single low-cost SDR to establish multi-network situational awareness of cellular networks in the local area. We've demonstrated that we can listen to multiple cells simultaneously and quite accurately count the number of devices within each cell. And we anticipate that our work there's many directions that our work can go in the future. Like the next thing that we want to do is downlink decoding. And so that concludes my talk. Thank you.
Okay. Do we have any questions? Questions from the audience? Okay, so I will ask one. If I understand correctly, there are control messages that different cell sends, and they can try to sometimes reschedule some of the devices and tell them what is the allotted time.
Yes, I might not have covered that adequately. So in this graph here, we are listening to something called the control, downlink control information in the cell, the DCI. And that is scheduled in every single subframe. And in that DCI, that contains scheduling allocations for both downlink data within that frame and future uplink scheduling grants. And so by listening to that, we can decode the radio network temporary identifier for each of these devices that are in the cell, and therefore be able to count the number of unique radio network temporary identifiers that we identify.
You target the downlink information of the controller for the cell and not trying to cover the uplink from different devices.
We're only listening to the downlink here.
All right.